what I want to get started today is with partial differential equations. We started with that, then we left because we had to learn the techniques of second order differential equations. So today what I'm going to do is fairly simple, but tomorrow and next class I'll do, the one where we have Bessel functions and stuff like that, and how to calculate the coefficient, to solve completely the problem, right? We just select the solution without getting, we wrote it in a very general form, the solutions to this. So what I want to do today is get started with this. Heat diffusion equation, which we have come across. What we want to do is we have a thin plate, semi-infinite plate. Okay. So this is semi-infinite. So the width of it is B here. And what we are given is these sides are kept at 0 degrees Kelvin, and there is this phase is, it has some temperature, and let's say it's also varying in this direction. Let's call this as our X direction, and this as our Y direction. Okay. So basically, it is this phase which is being heated, and you want to calculate the steady state temperature distribution subject to these boundary conditions. So we'll study this problem for 3 different cases. One when it's semi-infinite, okay, that will be case 1, we'll study. And then what happens, how does the solution change if I don't consider infinite, semi-infinite rod, but finite rod? I mean, what happens to that? So case 2, how finite plate or how does the solution change? And the third case would be we change the boundary condition, and how will the solution change? Okay. So case 3 will be change the boundary conditions. And we want to study the solution for each one of these cases. Now this is heat diffusion equation. Do you remember how it's, what's the PDE? We used to depict such a problem. Let's call this temperature as UXY. That's a variable temperature. It's a function of both X and Y. It's this thin plate. So U represents temperature. So supposing this variable represents temperature distribution, temperature. So what's the partial differential equation that in general represents what is the difference between diffusion equation and wave equation?
It's only a similar derivative. It's only a similar derivative.
On the right hand side, right? So the spatial derivative is the same, like del square of u xy is some constant, diffusion constant, 1 over. The right hand side is single partial of this temperature with respect to time. Okay? Whereas wave equation will have second partial of whatever this wave function, whatever it could be with respect to time. Okay? So that's the difference between wave equation, Schrodinger, whatever all those things will have, if it's time dependent, you will have, it will be different, right? I mean, so, or vibrational string, or, if you do that problem, it will be second derivative of displacement with respect to time, right? Okay, so that is your diffusion equation in general. What I want is steady state temperature distribution. Right? I mean, that's what we are going to get. So what simplification can I do? What is steady state?
The partial expected T is 0.
Yeah, the temperature, it doesn't change at each of the cross section, right? With respect to time, after some time, it'll sort of, becomes stable. That's what we mean, steady state temperature distribution. So du over dt is 0. So this becomes simply like a Laplace equation in this case. Right. Now, so what is del square here? This is a thin plate. How can I write del square here?
Only in y and x. Only in y and x.
Yeah, because we can use Cartesian coordinates, rectangular plate. So I don't need a cylindrical or spherical or any of the fancy coordinate system for del square. So I can write del square as a second partial of u with respect to x plus second partial of u with respect to y equal to 0. Okay, so it's as simple as that in a Cartesian coordinate, because the geometry of this plate is such, it's like that. By the way, this constant diffusion constant normally depends on the material property of that. So normally you have thermal conductivity, density of the material, specific heat and stuff like that. Okay, so that is, depends on the material that you're heating, right? I mean, so that constant will have, and of course it will have a unit which is I think L squared T minus 1. Yeah. Dimension of that will be like L squared. This is time, okay? So that's the dimension of because d will go up, it will be d squared dx squared, you can think of that, okay? L squared T minus 1, whatever it is, that will be the dimension of that diffusion constant. All right, so this is your PDE, right? U is a function of both x and y. This is a function of x and y. So how do we convert that into ordinary differential equation? Those are the boundary conditions, okay? Okay, how do we convert that into ordinary differential equation?
Assume separation of variables.
Separation of variables, so we have to write u of xy we say it's product of two functions, x and y. One term is function of x only and the other one is a function of y only. So when you do that, the first term we can convert the PDE into ordinary differential equation. So you have y d squared x dx squared plus x d square y dy squared equal to 0. So that's your independent variable, and x, y are functions. And divide by, the next step will be divide by x, y. Right. So you will get 1 over x d squared x dx squared plus 1 over y so this allows you to convert into ordinary differential equation. We had here PDE, right? But now we have, this depends only on x only. So we get ordinary differential equation. So that's why this step helps. All right, so up to this point, you know these steps. Write that. And what do we say next? What's the next step we normally do?
In other words, it's a constant.
Why? Because you also have to say because this is a function of x only, this is a function of y only. That's not possible. You cannot equate it unless each one is a constant. All right. So now the question is now, what constant, or what is the sign of the separation constant? This is called separation constant. So what's the sign of lambda squared? Should I choose plus or negative? Mathematically, both are possible. Okay, now we have a physical problem. Whether choose negative, you can do that. But now we have a very specific problem, so we have to choose the correct sign of the separation constant. If we chose negative lambda squared, what happens to this? 1 over x d square x. If I chose it as negative lambda squared, what is x as a function of x? Supposing you just chose, you do not know what to do, but let's say I chose this first. Then what does it, if I chose 1 over x, what does it say about x as a function of x? Sine, cosine,
E to the I.
or e to the I lambda x. Okay, is this a possible solution?
No, because it needs to decay.
It has to decay, so I cannot choose it because at x equal to infinity, this has to become 0, right? Because we have this, okay, and the temperature at x equal to infinity has to be 0. And if I chose negative lambda squared, I cannot because this is oscillating, right? So I cannot choose that. So I have to choose this as plus. Okay, that's how you have to rationalize. You have to look at the boundary condition, and that tells you what sign of the separation constant you can use, right? Okay, so, all right, so I can write x as a function of x as something, a sine lambda x plus b cosine lambda x. Oh, sorry, plus, so a exponential of lambda x plus b exponential of negative lambda x, okay? Because both can satisfy, right? Even with positive lambda x right now, I cannot even eliminate until we go to the next step, right? So because at x equal to infinity, this this has to be 0, this implies my constant A has to be 0. The only possible solution then, correct solution satisfying the boundary condition is then something like this. We have to determine all these things now, I mean, all of these things, because we got all the boundary conditions are there, so we'll apply one by one. So we applied one of the boundary condition, u at x equal to infinity, y equal to, this we have done, right? And this one is really u at x equal to 0 and any y is fy, and u at any x, y equal to 0 is 0, and this is nothing but u at x equal any x, y equal to b equal to 0, because that's the width of the split, right? So these are the 4 boundary conditions we have. So we are solving this problem subject to those 4 boundary conditions. All right. What else can we do? I applied this, and I will try to do that later, okay? Let's solve further the y part of it, at least get the general form of it, right? Since this is fixed, I cannot do anything, so, at least we know that 1 over, what we know is 1 over y, d square y, dy square is nothing but negative lambda square, right? This negative sign I'm taking there. Big Y. Okay, so what do we have? The general form of y as a function of y was the solution of this equation. It's oscillating, right? Yeah, that I can do that. C sine lambda y plus d cosine lambda y. Now I can apply these boundary conditions. Since u at x equal, this is 0, which means y, the big Y at y equal to 0 is 0. So we have this condition, y at y equal to 0 is 0. So that implies d is equal to 0. Okay, that coefficient has to be 0. So what we have is the general form, at least, y as a function of y, that must be oscillating. Okay, so I have applied this boundary condition now. Boundary condition 2 I have applied. I can start applying that, right? Y at y equal to b is also 0, okay, which implies sine of lambda b is equal to 0, right? All right, sine lambda b equal to 0 tells me something about now that constant, separation constant, right? What does it tell you about lambda b? Plus or minus n pi, right? That's what it says. Or lambda is plus or minus n pi over b. Right, that's what we have. But if I chose lambda equal to, this is my solution for x. If I chose lambda equal to negative n pi over b, it blows up at x equal to infinity. So even here, I have to negative will, so I have to choose this as a positive sign, okay? So we have further, elimination of everything, right? Because we have to, so I choose lambda equal to plus n pi over v. Mathematically, both are possible, but because of our physical situation problem, lambda has to be n pi over v. Okay, so one more screening we are able to do. All right, so now I can start writing this as n pi over v x, so we know that this is n pi over b times y. All right, so my general solution is then n takes on many values, right? 1, 2, 3, so it's an integer, n is an integer. So my most general solution has to be linear combination of all that. So the way you write your solution is b times c. Is there some, that's under constant, let's call it b big O n, okay. Exponential of minus n pi over b times x times sine of n pi over b times y, summed over n. So this is the most general solution of this problem. We still have to apply what? One more boundary condition we have not applied. I need to evaluate this also. Okay, everything they have to calculate. So let's apply the fourth boundary condition. So this is x, right? U at x equal to 0 and any y, right now we call it function y, at x equal to 0. So this term is gone. I'm trying to not evaluate b, b with n. I need to find a way to get that. So what I have is f of y people will write this from n equal to 1 to infinity because n equal to 0, that term is 0, right? Sign is 0. So, but that's obvious. Even if you calculated it, it automatically becomes 0. Even if you put 0, doesn't matter. It will become 0. But if you see it n equal to 1, that's the reason. Okay. I need to somehow, to get the complete solution, I need to find out what is this quantity, right? How do I calculate that? What does it remind you of?
Normalization. Normalization.
No, no. I'm just. You have some function which is written in terms of sine function, right? Does it say anything about f of y first? Okay, and when do we write a function in terms of sine or cosine? Okay, I mean all these things you start thinking to get this coefficient to be up there. So that's the point I was trying to drive.
Fourier series.
Fourier series, and also f of y is odd because it's written in terms of sine function, right? If I change sign, f of negative y is negative of f of y. So it tells me two things. It says f of y is an odd function. That's why I'm able to write it in terms of a sine. Okay. And this is a particular case which is called Fourier sine series, right? I mean, a Fourier series will have, oscillating function, write in the sine, a periodic function in terms of sine and cosine. But something like this, it's like a Fourier sine series. So I will develop that separately next time. I mean, in 2 lectures I'll do that so that you don't have, you cannot come across that. You know how to calculate these coefficients. But for now, just learn this, and if it is this, how through Fourier series, we know these coefficients are given by a certain formula which I'll write down, Fourier coefficients. So they are called as Fourier coefficients. Okay, I'll just write down like this and I'll tell you what they are, okay? Okay, if you have something like this, the coefficients can be extracted out through this formula. Okay, I mean, I will prove this to you next, in 2 lectures. Okay, when I'll talk about Fourier series. And, so what L here is the periodicity of the function, f of y. So, periodic function f of y is similar to sine, right? When does it repeat? So we have to not calculate coefficient. All I have to find out is what is L. Okay, rest then we can calculate. What is the periodicity of this function? We know it's an odd function and it repeats. Okay, at what interval is it repeating? We know the periodicity of sine function, right? So this is easy in Cartesian. This is the place where, when you go to cylindrical or spherical coordinates, to calculate this last coefficient b of n, if it's something, we have to know all the orthonormal property of Bessel function and all that, because this last part will take a lot of things. That's why we had learned all those things, right? I mean, orthonormal property and normalization property, Legendre polynomials and all those things. So, whereas in Cartesian coordinates, usually it's through Fourier series you can extract the coefficient. But in other coordinate system, you need to know the properties of the special functions and all other stuff. To extract the last quantity, if you want to get the solution, analytical solution. So how often does it repeat our sine function? What is the period of sine function?
N pi.
Huh?
N pi.
N pi or 2 pi? Multiple of 2 pi, okay? All right, because it is, that is, yeah. So we know this has to be a multiple of 2n pi, okay? So n pi over b times y, right? So pi and pi can cancel, so y is nothing but periodicity of the function f of y is 2b, okay? So So you'll also see in books, all it says is you have to integrate over one interval, okay? So it doesn't matter whether you started at 0 or you wrote it like that, doesn't matter. So you will, it gives the same result. I just want you to be aware of that also, okay? In fact, that's more, because it's more symmetric, that's how people would write it, but I just Okay, so if this is the case, my coefficient here will be now, I think about 2 over 2b, which is the, okay, and f of y.
Two B.
2b, right? I think there's a 2 here, sorry, I think, let me just, I have, I think this is 2 n pi over L, there's a, yeah, so this is here, sorry, this is 2 n pi here, I think, in this definition, I think when you have to get it, let me just check on this, I think. In the Fourier, you have to prove it, otherwise this is what happens, we go to Fourier series. Coefficients. Yeah, that is the definition of is 2 over L is 2 n pi to get the coefficient. That's what it is. Okay. Here this is what we get, but when you have to get the coefficient, it is 2 n pi over L. Okay. It comes. Yeah, I will prove this next time. Any general function can be written as a0 plus an cosine 2 pi n x over L plus bn summation of sine 2 pi n x over L. Okay, so there's a 2 factor there. So this is why I knew this is not the case. So that 2 and that 2b will cancel. Okay, so all right. So this is what it is, and this will cancel. And the other thing you have to notice is the following. This one, there's one more trick we have, because this is an odd function. You have to do it from minus b to 0 plus 0 to b, and when you do that, it really will become this integral is same as twice 0 to b. Or you can think of it as, okay, this is odd, the product is even, so let me just make it as 2 times 0 to b. Okay, so that's one more thing one has to do when you have an odd function like that. So b wiggle is 1 over b. Then you have twice coming from the fact the product becomes an even function. So this is the definition of Fourier coefficient. So we have to take the way it is. Okay, this is from the Fourier series definition. You extract the Fourier coefficient that way. So this is what I'll prove next time. Okay, so try not take it like that the way it is. So the function f of y has a periodicity of 2b, and this is the definition. So if you have a periodic function, you can extract the Fourier coefficient through this formula. Okay, so there's a 2 out there. Okay, so this is what we have. Okay, so we have all the stuff that we want. So we can plug that in, but I want to make a simplification at this point to get a nice form. So supposing the temperature here is a constant, okay? I mean, it's not varying along this direction. It is constant, T naught, then I can have a very simple expression. That's what I want to get. I can write this then we can integrate nicely. Right? This is what negative cosine, right? Negative cosine of n pi over b this is a negative sign, then you integrate that. And then I have b over n pi. This we have to evaluate between 0 to b. Okay, b and b will cancel. So what I have is minus 2z, 2t naught over n pi. And this term is what? Y equal to b, I have cosine of n pi. In the lower limit I get a 1, or I can write this as negative 1 to the power of n, right? So my Fourier coefficient Vn is nothing but minus 2t0 over n pi minus 1 to the power of n minus 1. Okay, so that's what it is. Which is 0 when n is even. So this contribution only when n is odd. Okay, so I get this as a factor of 2 I get, 4 when n is odd. So then for the steady state distribution, then what we have is this summation now has only odd terms, okay, because of that. And I can remove 4t0 over pi outside because that's now depending on n, the summation of n. I put this back again now because this is for any x, not just x equal to 0. So that's a solution of a heat diffusion equation with those boundary conditions. At x equal to infinity, that will become 0, it satisfies. And y equal to 0, right? That is on the horizontal axis, it should be 0 and all that, and the other coefficient, of course, f of y, so they've checked all that. So that's the general form of this this is steady state solution of this equation for that thin bar with those boundary conditions. Okay? So the question is now, it's not semi-infinite. I'm going to say, well, it's a bar, this length is a, and it is 0 for u at x equal to a and any y is 0. Supposing I change the boundary condition from this to that, how does the solution change? So only thing I've changed is that. So what is u of xy? Just one change that I've made. This is still true, right? I mean, now. At this point, this is still true. I mean, so I want to find out what is this. Can you guess a solution in the y direction?
Very similar solution to the, in the y direction?
Mhm.
Same.
Same, nothing will happen in y direction, we will not change anything, okay? This x direction is going to change. Okay, so we said this is equal to, whatever, plus or minus lambda square, right? Again, we had to go through the whole process. We chose negative still will not oscillate still, okay, it has to be plus. But the separation constant must have a plus sign. But if I do that, I have to also make it at x equal to a go to 0. So what is the functional form should I choose so that, it was previously very easy because I could drop exponential plus x, I only had to take exponential negative lambda x, which was, it will become automatically equal to 0. Do you know what a combination of exponential lambda x and negative lambda x will, what function it will lead to? If I combine the superposition of lambda x and negative lambda x. You know what happens with exponential I lambda x and negative lambda x, right? If we combine them, positive or negative, whatever it is, you know what function that leads to. Right, because exponential I lambda x I can write in terms of sine lambda x and plus I cosine lambda x, and depending on how the superposition, when you can have a sine or cosine function. So similarly, you have to think similarly here. If you combined lambda x and negative lambda x, what all functions can you get? What trigonometric function can you get? Do you know any trigonometric function that will lead to, if I combine, I know I'm choosing plus lambda square, okay? That is there, and I have to first choose a functional form, and also it has to become 0 at x equal to a. Those are the two things I need to somehow satisfy to give a functional form for this. So do you know what this function is? If I had this, or yes, so it's a combination of cosine, it's a hyperbolic function actually. It's a combination of sine, and that's why I want to think of exponential then. So if you put in lambda as I lambda or x equal to ix in the original expression, it becomes, you can convert a sine to a sine hyperbolic with some factor I or something, cosine become directly cosine hyperbolic. Okay, so I can write this as a cosine hyperbolic, but I want it to go to 0 also at x equal to a, right? So I will write it as a minus x. There's a lambda also, right? Lambda x, right? So I can put it there or here, it doesn't matter. Ax, whatever you want. Lambda x, it's like a factor. So let me put it here. So that's a function. Hyperbolic plus b sine hyperbolic lambda ax. So that linear combination of function at x equal to a, this has to be 0, right? Sine hyperbolic at x equal to 0 is 0 because it's exponential x minus lambda x, so it will become 0. So I have to set a equal to 0. Okay, so for that condition to satisfy. Okay, so
How would we know it's a minus x and not x minus a?
because A is, because A is larger, and X is a running variable, right? So I'm putting an A minus X because I want it to be, A is larger than X.
You want it to be positive both times.
Yeah. All right, all right, okay, this implies A is equal to 0. So the function form is then B sine hyperbolic lambda A minus X. So that's the change here. Okay, instead of exponentially decaying, it is the sine function. The y direction you can do it, but nothing is going to happen. It'll be, you can do repeat it because nothing has changed, right? I mean, so it'll be exactly the same solution. So y direction is simply, I'm not going to, yeah, because everything came from the y direction, I can also have this lambda equal to n pi over b. Okay, it's going to be the same. So lambda, because nothing has changed in the y direction. Okay, so c and sine is lambda b. Let me write lambda b, but lambda is n pi over b for the same reason what we had before. Okay. So lambda is n pi over b as before. So the solution is the following. The general solution will be, once I put n, because n can be anything, it's a product of b and c, which I can call it some, I'm just calling it bn, doesn't matter, some coefficient that I have to evaluate. Sine hyperbolic n pi over b a minus x. This is small x, okay, that function. Times sine of n pi over b lambda. Alright. So we still have to calculate this last coefficient in this problem. So what we are going to do is the following. The last condition is that this n, which is x equal to 0, what happens, right? So this is the boundary condition we have not applied. All these things we have applied now. And so u at x equal to 0 and any y, we'll call it f of y initially, is nothing but bn sine hyperbolic n pi over b times 0, x equal to 0 already put, okay? So this is the fourth boundary condition. All right, function of y right now n is all n, right? Can we calculate what I've circled? It's a constant, right? I mean, sine hyper, all that. There's no function of x or y. So it just you can think of that bn times sine hyperbolic of n pi something. It's just some number, okay? So I can call this as some other coefficient. So then I know I can still apply the Fourier series, and I calculate b and middle, and then once from there I can calculate bn. If I know that, I can calculate that. Okay, that's what we'll do. All right, again, the periodicity of this function is 2b, right? It's the same thing. So periodicity of f of y, nothing has changed. So we'll go back to, so I'm going to calculate Bn wiggle. Okay, Bn wiggle is nothing but, we have to integrate over 1, I said, what did I say, 2 over L, right? Integrate over 1 period, in this case 0 to 2b or minus b to plus b, doesn't matter, okay? That's the integration over 1 period. This function f of y, sine of, is there, 2n pi y over the periodicity of the function, which is L, which is 2b, okay? So this 2 and 2 we can cancel. So the rest will be the same, similar thing, except now that we already calculated it, right? So you know how to do that. And this is again twice of 0b, we can write it. So this is same as 2 times 4b, 0 to b, f of y. Okay. So I mean, let's again make it as a constant, then you know how to do it, and then you get a simple function. So if this was a constant, d naught, then Bn wiggle would be simply T0 over b, and same thing, right? I mean, cosine of n pi, you will have that as well. The first term will be cosine of n pi y over b over, what is that? B over n pi, right? B over n pi. You evaluate between 0 and b. That's what it is.
It should be negative, right?
Negative sign will get, yeah, and that negative sign. So Bn wiggle is nothing but b and b can cancel. So negative 2 t0 over n pi. The numerator will be again cosine of n pi, which I can write as negative 1 to of n minus 1. Okay, same thing. You get 4t. It's negative sign, so negative. This will be negative 2, right? Then when is equal to r. So you have 4t0 over n pi. So once you have that, okay, for n equal to r, okay, otherwise it's 0. All right. So once you have that, we do have Bn because the relationship between them is what? Bn sine hyperbolic of, it depends only on the dimension of the plate, right? Or the width and length of the plate. That is equal to B wiggle, and wiggle, which is 4t0 over n pi. N is odd. Or Bn is nothing but that quantity. So Bn is nothing but 4t0 over n pi. So instead of, we had only previously we had it as 4t0 over n pi. That was my Bn, but now you got this extra factor. This was not there before, right? Previously we had this for Bn. Okay. So the full solution will be then the following. So this will become now only n equal to r, not all n. That will be one change, and the rest will be same. and then all that is also there. So it's in the denominator, so I'm going to write it like this. Okay. Maybe we can write it like this. All right. So the changes are here. This function changed, function of 1. Okay. And this factor also changed when you went from infinite to a finite rod. All right. So I'm going to make one more change. So we have again. So this is a finite plate, but I'm going to change the boundary condition. It's 0 here. These spaces here. There is the temperature. On that side, which is at what x equal to u at any x, y equal to b is g of x. Okay. And then we have this u at x equal to 0 and any y is f of y, right? And of course the others are u at any x, y equal to 0 is 0, and u at x equal to a, and any y is 0. So we want to find what's the solution in this case. Can you just guess the solution? Based on what we have done thus far.
The x component's going to look like the y component we did last time. Or sorry, the other way around. The y component this time is going to look like the x component we did last time.
Mm-hmm.
So we're going to go the same
A
form.
and B and everything that has to be there. So what I want to tell, this, we have more complicated boundary condition. This problem, we can view it as the solution for, this is what we did first, right? This is what we have done just now, okay? This is exactly same as so let me call this as, this is what we, let's say the final solution is the x, y I want to calculate. And so the solution, this is a problem, finite rod, and the boundary, all of the sides, 3 sides are 0, temperature is held at 0, and one side, is non-zero, right? So this we have already gotten, and in order to get that, all I have to do is flip the sign, right? X to y, A to B, right? You will get the solution. So superposition of this and that will be the solution. But you can, of course, solve it, brute force. But I'm just saying, for a simple boundary condition like this, you can, if you solve a part of the problem, you can start guessing the solution. Okay, so that's what it is. So your what we call as U is now B, right? And WXY would be just So they put A as B, B as X as Y, and stuff like that. Oh, sorry, I got a denominator too, and I'll come to that in a minute. The sine of n pi over A times X, okay? And then what was the denominator? We have to get that. Do you remember the denominator, what it was? I mean, we have to flip the signs there. Was it this? Yeah, n sine of the hyperbolic n pi. So basically, you know, A became B, B became A, X became Y, and Y became X. Because the way the boundary conditions are. So you could explicitly do it, but I'm just saying you can just get it this way, or even if you wanted to do this explicitly, you can do it. But I just want you to have an idea how we can. Any questions? Alright, so in Cartesian coordinates it's simply the only, it's simple. It goes step by step. The only thing you have to know is Fourier series, in this case, to calculate the last coefficient. Previously, we just left the solution very generally because we did not know the boundary condition, what is the problem we're trying to solve. But if you know the physical problem, you know everything, like the vibration of a string, a simple string. I mean, both ends are fixed. It is not, so you know the boundary conditions, right? So you can calculate them depending on if your initial conditions also given, then you block it and you know how the displacement has to be and stuff like that. So in this case, it's fairly simple. It becomes complicated when del square is expressed in cylindrical and spherical coordinates. Okay, all right. So we'll do something a little bit more complicated next time, but this is just to get you started. And also we did most of it previously, separation variables. So, but we're just solving it exactly now. So that is an analytical solution. You can do it numerically. So some cases like this, you can do it and check your algorithms, numerical algorithm, right? How good it is. Because we have an exact solution, you can choose it or a certain length and start doing it. And you can check the quality of your algorithm and stuff like that. So you do need some, exact solution in some special cases. To check your, because then you can do more complicated boundary condition and stuff like that. You don't have to have a constant and all that, right? You can really put f of y as it is varying and all that. So you can do more and more complicated problem once you know your algorithm is correct. I mean, that would be the realistic situation most of the time, right? I mean, it's not going to be that simple. But for analytical solution, this is a way to do. All right, I'm going to stop here today and get started with the heat diffusion equation in a cylinder or something, cylindrical geometry next time. Then I'll start doing Fourier series, okay, and then so that I just wrote that expression, but you at least know where the Fourier coefficients are coming. And we'll start talking about how we can represent a function. Fourier series you can represent for a periodic function, but in general a function may not be periodic. Then how do you represent a function? So we go to Fourier transform, Laplace transform, and all that. Different types of transforms represent the function. So that's what we do, and then the last part will be complex analysis. But this will tie with the Fourier series, so that way you know how to solve it. Where we got that expression from, the Fourier coefficient expression, the integral that I wrote.
for the one.
Yeah, just that troublemaker.
Yeah, several pages.
Two class periods of lectures to cover that.
Saw one problem. What was the first problem?
It's like you're watching a TV show and then you get to a character and then they have some backstory that you have to explain. It's like, all right, now we can get back to the main stuff.